So the thing that we are going to see today is the theorem of the calculus of single complex variables, okay, and that is the residue theorem. We are not directly going to state the theorem, the residue theorem. We are first going to define the residue, okay, and then we will see how the residues are connected with integrals along closed curves, okay, and then of course we will see examples to calculate the residue. Okay, now this has something to do with the formula for finding Bn. Okay, remember if we let n to be 1, okay, that is B1, then the integrand simply reduces to f of z. Okay, because it is f of z times z minus z naught raised to n plus 1, and if we let n to be minus 1, okay, here, then it becomes 0. Okay, so the only term that we have is f of z, and this is the connection between the integrals and the residue. Okay, but we will see that later. Then in addition to these methods of obtaining the coefficients, okay, we also have methods to obtain residues. Okay, now the methods that we are going to see, these are applicable only to non-essential singularities, meaning these methods will work only when the Laurent series consists of finitely many terms which have negative integral powers of z minus z naught. Okay, all such singularities are called as non-essential singularities. Okay, and we are going to develop two formulas to find the residue at a simple pole or a pole of order 1, and then we are going to develop a more general formula to find the residue at a pole of order k, which is usually any integer greater than or equal to 2, and at last we will state the residue theorem. Okay, so this is going to be the first part. Once we see the residue theorem, then we will directly go to the problems. Okay, we will solve the contour integrals, that is, we will solve all those problems which we were solving by the Cauchy's integral formula, and then we will see how we can use the residue theorem cleverly to actually solve the real integrals. Okay, meaning functions which are defined only for real numbers. Okay, fine. So we will be primarily focusing on two types which are more frequently asked. Okay, first is when the integrand is a rational function of the sine and the cosine functions. This is by far the most commonly asked problem type, and there are other problem types involving the improper integrals which we will see later. To begin with, let us see the definition of the term residue. Okay, now the term residue has something to do with isolated singularities. So let us first recall what an isolated singularity is. Okay, so we say that z equal to z naught is an isolated singularity of f of z when in some neighborhood of z naught, that is, let us say in this particular neighborhood there is no other singularity apart from z naught. Okay, hence the word isolated. Okay, there is at least one circle of non-zero radius which only covers that singularity. Okay, so residues are related to only isolated singularities. Okay, so we are now going to start with the Laurent series. Okay, we are going to consider the function f of z which has an isolated singularity, the one which we discussed here, at that point z0. Okay, now this means our function is going to be not only defined but is also going to be analytic on this particular disk, okay, or cylinder, sorry, not disk, not cylinder, a circular region, okay, with its center being omitted. So we are going to consider all those complex numbers which lie there except the center, okay, and with the Lorentz series given by the usual two parts. You can see the principal part here, and you can also see the regular part or analytic part here. Okay, and because we have said that the function possesses an isolated singularity and we are expanding it in this particular region, okay, it is going to be analytic everywhere. Okay, now what we will focus on is the coefficient b1. Okay, we know that the principal part when expanded becomes b1 into 1 upon z minus z0 plus b2 into 1 upon z minus z0 squared plus b3 into 1 upon z minus z0 to the power 3 and so on. Okay, this is the principal part, and we are going to define the residue of the function f at the isolated singularity z0 to be the coefficient b1. Okay, this one, and we denote it by res bracket f comma z0 or res of f at z equal to z0, which is b1. Okay, for instance, let us consider the function e to the power 1 upon 2z. Okay, so we are now going to substitute 1 upon 2z as t and obtain the Taylor series about the number 0. Okay, so that gives us the following series. Now observe that this particular Lorentz series consists of only one term in the analytic part. Okay, that is a0. a0 is equal to 1 and all other ans are equal to 0. However, there are infinitely many terms in the principal part or singular part. Okay, we are interested, as far as the residue is concerned, we are interested only in the coefficient of 1 upon z minus z0, which is going to be 1 upon 2, and therefore the residue of the function f of z defined by e to the power 1 upon 2z, okay, at 0 is 1 upon 2. Okay, so the residue is essentially the value of the coefficient b1. Okay, now let us try to compute this particular integral. Okay, the integral is sin z upon z to the power 4 and the contour of integration is c, which is the unit circle mod of z equal to 1. Okay, now is it possible to find the Lorentz series expansion of sin z upon z to the power 4 about z equal to z0, which is 0? Yes, because this is now an isolated singularity of the function sin z upon z to the power 4. Okay, now we will use the Maclaurin's expansion of sin z first, which will be the bracket z minus z cubed upon 3 factorial plus z to the power 5 upon 5 factorial and so on, and we are now required to multiply this by 1 upon z to the power 4. Okay, now this allows us to change these powers. Okay, So the first term is now going to be 1 upon z cube. Yes. So the coefficient of 1 upon z cube is 1, that is b3. But as per the definition, we are not interested in the value of b3. Okay, so let us go to the next one, which is negative z cubed upon 6 or 3 factorial. So if you now multiply this by 1 upon z to the power 4, what will you get? You will get negative 1 upon 6 into 1 upon z. Yes, okay. And are we now in the term which has the negative 1th power of z minus z naught? Yes. Which means this term is now going to give us the residue. We will go to the coefficient of 1 upon z in that term, which is minus 1 upon 6, and this is the residue of the function sin z upon z to the power 4 at 0. Okay. Now we also note that because you have z to the power 3 here in the denominator, okay, by the definition this is going to be, this won't be a simple pole, but this is going to be a pole of order 3. Okay, and we also recall the formula that we use to find the coefficient b1. Okay, the formula to find the coefficient b1 is 1 over 2 pi I into the integral of f of z into z minus z naught to the power n minus 1, okay, where n is the subscript here. And because here we are finding b1, this subscript will be equal to 1, and now observe that 1 minus 1 is 0. So what we have is actually 1 upon 2 pi I into the integral along c of sin z upon z to the power 4, and we have already obtained b1 by the Laurent series, okay, which is negative 1 upon 6. So we have not computed the integral, so to speak, right? So integral's value is now going to be 2 pi I times negative 1 upon 6. Okay, you just shift 2 pi I to the other side, which will then give you the value of the integral as minus pi I by 3. Okay, which means so far it appears to be the following. Step 1, get the Laurent series. Step 2, find the coefficient b1. Step 3, the value of the integral of the function f of z, okay, with respect to z is going to be 2 pi I times b1. Okay, this is what this problem has told us, or you can say that it is 2 pi I times the residue. At z naught. Okay, so C is any closed curve which encloses z naught, and the function is not defined at z naught, okay, or is not analytic. Okay, it is an isolated singularity. Okay, now this particular problem is very simple, okay, for two reasons. The reasons of simplicity are as follows. Reason number 1, there is only one isolated singularity in C, okay, which is the center itself in this particular example, because C was the unit circle. Okay, and point number 2, Laurent series was easier to obtain. Okay. However, it turns out that as we go on solving more and more complicated examples or complicated functions, okay, we may not always have the situation where we have only one isolated singularity in C. Okay, so if we have even two isolated singularities, then we cannot go with this particular procedure which we have gone for in this particular example. Okay, and well, we exactly have the residue theorem exactly for that, which applies not only to the functions which have just a single isolated singularity, but also to functions and curves which include more than one isolated singularity but finitely many isolated singularities. Okay, now the second point is more important. Okay, although we have now defined b1 to be a residue to be the coefficient b1 of the Laurent series at that particular center, it turns out that except b1, okay, this one, there is no reason to actually calculate the other coefficients including all ans and all bns. Okay, so now on what we will do is, from now on we will try to develop methods to just calculate b1 exclusively. Because although we have defined residue to be the coefficient b1 of the corresponding Laurent series, we don't actually need the entire Laurent series of the function. Okay, so let us now try to obtain formulas to find the residues, okay, or b1 without actually computing the Laurent series. Yes, so the calculation of residue, or I would say this. Okay, when you defined residue, you defined it using the Laurent series. However, the computation of entire Laurent series is not necessary. Okay, what you need is just b1. Knowing b1 is enough. So what we do is we now develop a method, or methods I would say, to evaluate the residue, that is the coefficient b1 and not the other coefficients. Okay, we now take a note of this fact. Okay, the formulas that we are going to develop, these are not applicable for essential singularities. Okay, so let us remind ourselves what an essential singularity is. Okay, for an essential singularity, the singular part consists of infinitely many terms, which implies that infinitely many bn's are non-zero. Okay, now the definition of residue still holds. Okay, as long as the singularity is isolated, the residue is still going to be the coefficient b1. However, the methods that we are going to develop now, these will be applicable only for non-essential singularities or for those functions which have finitely many terms in the singular part of their Laurent series expansion. Okay, fine. And when we solve the problems, in all of them we will be having non-essential singularities. Okay, if your professor covers problems with essential singularities as well, then you have to first find the Laurent series and then go to b1. Okay, but it should always be an isolated singularity. That's the main point. Okay, the formulas that we will now see, or which we will be deriving, these are only shortcuts. Okay, fine. We will start with the simplest case, that is a pole of order 1, often termed as a simple pole. Okay, so we have an analytic function f of z, and z naught is an isolated singularity. And it is known that it is a simple pole, and our objective is to find B1, that is the residue. Okay, what we do is we first write down the Lorentz series about Z0, and here by writing down I don't mean we already know the values of B1, A0, A1 and so on. Okay, we'll just do it for the sake of it. Okay, now this being a simple pole, for all n greater than or equal to 2, Bn's will be 0. Okay, because it is a simple pole. So in the singular part or the principal part of the Lorentz series, we will have only one term, which is this one. All these terms will be will form the analytic part or the regular part. Okay, yes. Now the main thing here is you have to multiply by z minus z0. You multiply the entire Lorentz series, not only the right hand side but also the left hand side. Okay, so if we do that, then we will get z minus z0 into f of z on one side, and on the right hand side we will get b1 plus a0 into z minus z0 plus a1 into z minus z0 squared and so on. Okay, and more importantly we take the limit as z tends to z0. Now if we take the limit, this is what is going to happen. Okay, limit as z tends to z0 of z minus z0 into f of z will be now equal to limit as z tends to z0 of the entire Lorentz series multiplied by z minus z0. Okay, so all these terms will have an additional power of z minus z0. So b1 will no longer have z minus z0 in its denominator, okay, or as the coefficient. So this will actually give us just b1, and then a0 will have first power, a1 will have second, and so on. Okay, and the reason for taking or obtaining the limits is that if we take the limit, then these terms will go to 0. Okay, after taking the limit, and therefore we have now got the formula to find the residue of f of z at a simple pole or pole of order 1. Okay, and the formula is residue is limit of z minus z0 into f of z as z tends to z0. Let me again remind you that there are two conditions here. Condition number 1, z0 is non-essential singularity. Or a pole of finite order, and more importantly here it is a simple pole. Okay, then this is the formula. Now sometimes we get an indeterminate form, let's say 0 by 0, there we can use the L'Hospital's rule. Okay, so we'll differentiate the numerator and the denominator separately and then calculate the then find the limit and hence and thereby obtaining the residue. Okay, let us solve two examples. Example number 1. Here our job is to calculate the residue of the function f of z at z0, which is I. Okay, now observe that the denominator of this rational function is z cubed plus z. Okay, now when you equate z cubed plus z to 0, you get z into z squared plus 1 equal to 0. Okay, which means this particular function f of z has 3 isolated singularities. Okay, the first singularity is 0, the second singularity is I or iota, and the third singularity is negative 1. Okay, and all 3 are isolated. Yes. Then it is asked to find the residue of this function at z0 equal to I. So we will now make use of the fact that it is a simple pole and use this formula, okay, or a pole of order 1. So the residue will be given by limit as z tends to I of z minus z naught into f of z. Okay, cancel the factor z minus I and substitute z equal to I, because this is now not in the indeterminate form. Okay, so 8i minus I, 7i, z into z plus I will be I into 2i, okay, or minus 2. So the residue of this function at z equal to I is going to be negative 7i upon 2. Okay, now let us see when are we required to apply the L'Hospital's rule. Okay, question 2. Let us say we are interested in finding the residue of the function f of z at the point z not equal to I, the same point. Okay, the function is again a rational function, 1 upon z to the power 4 minus 1, and now we observe that this particular function f of z has 4 singularities. These 4 singularities are when z to the power 4 is equal to 1, so 1, minus 1, I and minus I. Okay, and note that all 4 are isolated. Okay, and we have to find the residue of the function f of z at one of the 4 singularities, and that is I. Okay, so residue is now limit as z tends to I of not the function f of z but f of z times the factor z minus z naught or z minus I. Okay, now did you notice that here we are getting the indeterminate form 0 by 0? Yes, we are getting the form 0 by 0. Okay, I minus I is 0, I to the power 4 minus 1 is also 0. So now apply the rule, the L'Hospital's rule. Okay, so derivative of z minus I with respect to z will be 1. Yes, derivative of z to the power 4 minus 1 with respect to z will be 4z cubed. Yes. Okay, now we can substitute z equal to I there, so I cubed will be minus I. Okay, I mean it is in the denominator. Hold on, let me check this. We will get 1 upon 4 into negative I. 1 upon I is minus I. Yes, I think the answer is I by 4 and not negative I by 4. Okay, so let me correct it. Yes, because 1 can be written as I to the power 4 and here we have 4i cubed. Yes, so it is I by 4 and not minus I by 4. Okay, that was my mistake, but we have corrected it. Okay, so this is how we find the residue by not generating the Laurent series, provided the pole that we have is a simple pole, okay, or a pole of order 1. We may be required to apply the L'Hospital's rule in some cases. Okay, now let us see how we can find the residue at a pole of higher order. Okay, fine. Calculating residue at a pole of order k greater than 1. And for this we recall the definition of the pole of order k. Okay, so we define a pole of order k to be that singularity z0 where if the function is expanded about that point in Laurent series, if bk is not equal to 0 and bn, all bn's are 0 when n is greater than k, then we say that z0 is a pole of order k. So this is still a non-essential singularity, but the largest power of 1 upon z minus z0 is k. Okay, all right. So to calculate the residue, obviously we should be given the things f of z, then the pole and the order of the pole. Okay, now usually it is very easy to find the order. Let's say if we have the factor 1 upon z minus z naught to the power lambda, then this becomes a pole of order lambda. That's what happened even in our previous two examples. Okay, z minus I was the only factor in the denominator whose power was 1, so the order of the pole was 1. Okay, now we start our derivation by writing down the Lorentz series, okay, of the function f of z obviously, but this time about z naught. Okay, and because we know that this particular pole z naught is a pole of order k, we will not have any powers of z minus z naught which are less than minus k. Okay, so the very first term in the Lorentz series expansion is going to be bk upon z minus z naught to the power k, and then eventually the powers will start increasing by 1, and once you reach b1, the principal or the singular part will be over, and then from this we will have the analytic part. Okay, now if you remember the procedure, there we multiplied by z minus z naught because it was a pole of order 1. Now we are multiplying by z minus z naught to the power k because this is a pole of order k, but we are not taking the limits. Okay, the reason will become clear very soon. If we multiply both sides of this by z minus z naught to the power k, we will get the following: f of z into z minus z naught to the power k equal to bk plus bk minus 1 into z minus z naught, and so on. Okay, so every term will acquire an additional power of z minus z naught, which will be the kth power. Okay, now you see the reason why we do not take the limits. Okay, the reason is very simple. Had we taken the limits, we would not have got b1, but we would have got bk. But are we in search for bk? No, we are not in search for bk, we want b1. Okay, so taking the limits may be a valid operation, but we are not interested in that. Okay, but what we now consider is this: although the function f of z has an isolated singularity at z naught, okay, or a pole of order k, when we multiply f of z by z minus z naught to the power k, we are actually cancelling that particular power in the denominator, isn't it? Z minus z naught to the power k, which now means that we can have the Taylor series expansion of the function f of z into z minus z naught to the power k, okay, about z naught, isn't it? Okay, now this particular thing b1 is the coefficient, not the first coefficient or the second coefficient, it is the coefficient of z minus z naught to the power k minus 1. Okay, observe that initially the coefficient of b1, the power accompanying b1 was z minus z naught to the power minus 1. Okay, but due to the multiplication by z minus z naught to the power k, the power of z minus z naught in the b1 part became k minus 1. Okay, and because the first term doesn't contain any power of z minus z naught, we can now consider this to be the Taylor series of f of z into z minus z naught to the power k, and due to the uniqueness property of the Taylor series, we can actually get the formula for b1 by comparing it with the coefficient of z minus z naught to the power k minus 1. Okay, and we very well know how to find these coefficients. Okay, in Taylor series we use derivatives. So b1 is going to be 1 upon k minus 1 factorial multiplied by the value of k minus 1th derivative of the function f of z into z minus z naught to the power k at z equal to z naught. Okay, let me let me write down the Taylor series expansion of f of x, let's say, about a. Okay, so the first term is f of a, the second term is x minus a into f prime a, the third term is x minus a bracket squared upon 2 factorial into f double prime a, and so on. Okay, so if we have the nth power, then it is x minus a to the power n upon n factorial into nth derivative at a, and so on. Yes, but this time we don't have the nth power, we have k minus 1th power, and therefore when we replace this n by k minus 1, okay, then we have 1 upon k minus 1 factorial multiplied by the derivative of the function, the k minus 1th derivative of the function at a, and in this case x is being played by z and a is being played by z0. Okay, so this is how we get the formula for b1 at a pole of order k. Remember, although it is a pole of order k, we do not take the kth derivative, we take the k minus 1th derivative, and also we take the derivative of f of z into z minus z0 to the power k. Alright, now we'll see whether this fits into the old formula for b1 where k was equal to 1. Well, yes, it does fit. Okay, because there what we had for b1 was simply the limit as z tends to z0 of f of z into z minus z0. Okay, because k is now equal to 1, so it fits because it is 0th derivative. Now 0th derivative of any function is the function itself. Okay, now usually in the problems what we have is both first order poles as well as higher order poles, and if it is a first order pole we may be required to use the L'Hospital rule, and if it is a pole of higher order, use this particular formula. Okay, and don't forget k minus 1 factorial present in the denominator. Okay, and see, at the end you have to substitute z equal to z0 in whichever function you get as the k minus 1th derivative of the product. Okay, now let us quickly see an example. Evaluate the residue of the function f of z given by 1 upon z plus 4 into z minus 1 bracket cube at z equal to 1. Observe that this is again a rational function, and this particular function has two isolated singularities. The first one is at negative 4 and the second one is at positive 1. Okay, now due to the first power of z plus 4 in the denominator, k is going to be 1 for z equal to minus 4, and k will be equal to 3 for z not equal to 1. Okay, because of the third power. So if we are to find the pole at z equal to 1, we will now, well, if we are to find the residue at this pole, which is the coefficient b1, we recall this particular formula: 1 upon k minus 1 factorial 1 upon 2 factorial into k minus 1th derivative of the function multiplied by that particular factor, z minus z0 to the power k. Here it is z minus 1 to the power 3. Okay, which means it will lead to the cancellation of this particular term. Yes, so we are now to find the second derivative of 1 upon z plus 4 at z equal to 1, which we can very easily do. Okay, 1 upon z plus 4's derivative will be negative 1 upon z plus 4 bracket squared, and again its derivative or the second derivative of this function will be negative 1 into negative 2 upon z plus 4 to the power 3. Substitute z equal to 1, so it is going to be 1 upon 2 into 2 upon 125 or cube of 5, 2 will get cancelled, and we will have 1 upon 125. So this is b1 now. If we were to find the Lorentz series expansion of f of z about z equal to 1, then the coefficient of 1 upon z minus 1 would be 1 upon 125. Okay, so we have now seen three formulas. This formula is applicable for pole of order k, and the two formulas that we had developed earlier, these are applicable for simple poles. Okay, if that limit is well, if the limit is such that if you substitute z equal to z naught in that function, if you're getting an indeterminate form or 0 by 0 form, usually then use the L'Hospital's rule. Okay, so we now have everything. We know what the residue is, okay, which is the coefficient b1 of the Lorentz series, and more importantly, we know how to actually find the residue indirectly, okay, or implicitly, not by finding the actual Lorentz series of the function. And then we also know why do we need b1. The need to find b1 exclusively is that if we go to the formulas for finding bn's in the Lorentz series and substitute n equal to 1, what we get is this. Okay, and this is exactly what we are looking for. Okay, so now having seen the residues and the formulas to calculate the residues related to isolated and essential singularities, we will now state the theorem. Okay, now this is the theorem, meaning you can solve all problems which we solved by the Cauchy's integral formula and the residue theorem, integral theorem, okay, which we called the Cauchy's integral formula and Cauchy's integral theorem respectively. Sometimes, to avoid the confusion, the residue theorem is just called residue theorem, not Cauchy's residue theorem, but both are essentially the same. Okay, Cauchy's theorem is different, okay, and Cauchy's integral formula, they are different, but Cauchy's residue theorem is also sometimes called as simply residue theorem. Okay, so what are the things given in the residue theorem, meaning when can we apply the residue theorem? Okay, we are given a function f of z and a simple closed path c in the z plane. Okay, it is also given that f of z is analytic on c, meaning no singularities are permitted on the curve. Okay, fourth, f of z is analytic inside C except for finitely many singular points z1, z2, so on till zn. Okay, now the fourth thing is important. Okay, it is allowing finitely many singularities. Okay, so you can have 2, 3, 4, n number of singularities, but not infinitely many singularities. Okay, and except for those singularities, it is an analytic inside. Okay, these are the conditions. When these conditions are satisfied by the given things in the problem or in the question, then you can apply the residue theorem. Okay, now the conclusion of the residue theorem is this. If we are interested, well, of course we are, in finding the integral of f of z along that simple closed path C, it is given by multiplying 2 pi I by the sum of the residues of the function f of z at all the singularities which are inside C. Okay, so we will find the residue at z1, we will find the residue at z2, we will continue this till we reach zn. We will add the residues and we will multiply the addition by 2 pi I. That will be the value of the integral. Okay, now in this particular part, the only thing that we need to compute is the residue, and we have exactly developed formulas for that. Okay, if it is a simple pole, then the formula to find b1 or the residue is simple. Just take the limit of the function z minus z0 into f of z as z tends to, well, not 0, sorry, z tends to z0. Okay, if it is a simple pole, you may be required to apply the L'Hospital's rule. Okay, and excuse me, and if it is a residue of, well, if it is a pole of nth order, okay, z equal to z0, then you find the residue by the other formula which we obtained. Okay, 1 upon n minus 1 factorial into n minus 1th derivative. So here d is the operator d by dz, n minus 1th operator of n minus 1th derivative of, not f of z, f of z multiplied by z minus z0 to the power n, and we first compute the derivative, and once we complete it, we substitute z equal to z0 to get the residue at that particular, I would say, the center of the Laurent series. Okay, now there is one more point which we should take a note of. F of z may have infinitely many singular points or singularities outside C, but these singularities will be irrelevant to us. We have seen that functions like tan of z or sine of, well, tan of z may have, do have infinitely many singularities, but it all depends on what closed path you have. Okay, so again, if a function is presented to us, we will be required to locate the singularities. Okay, we should not have even a single singularity on the curve, and we should have only finitely many singularities or singular points z1 till zn. Okay, and once we classify the location of the singularities with respect to the curve, inside or outside, we will not calculate the residues at those singular points which are outside C. Okay, now the thing is, when is the residue theorem preferred over the Cauchy's integral formula? The residue theorem is preferred when we have more than one singular points. Inside C. Okay, if we have only one singularity, inside C, then both the Cauchy's integral formula and the residue theorem, they produce the same result, of course. Okay. And if you still insist that we are to solve this problem by the Cauchy's integral formula, then what you are required to do is you are required to split it into the function upon z minus z naught, well, let's say raised to n, plus a different numerator upon z minus z1 raised to, let us say, n prime, and so on. Okay, so you have to split it into a lot of partial fractions, and hence the use of Cauchy's integral formula, if we have more than one singular point inside C, is not recommended. Directly go to the residue theorem. Okay, fine. So we have now stated the residue theorem. We have also seen three formulas to find the residues. Now let us go to the problems.